Now that you all are experts on populations and different things that can change the population size, we're going to do your favorite thing. That's right. We're going to do some math and biology. Woo, woo, woo. All right. So we've got some equations here. These are our population growth equations. This is on the back side of your AP Bio equation sheet. It looks worse than it is. Okay. So a couple of things I want to point out. Um, is we're going to be primarily like using these bottom three ones. Okay. B is birth rate, D is death rate, N is population size, K is carrying capacity. And this R max here is the maximum per capita growth rate. So just what that means is by how much can this population increase every generation? Okay. Um, and this population growth is just saying, hey, how much does population growth grow by? What's our change over time? Oh, we're going to do births minus deaths. Okay, so it's not that bad. So you'll notice that this dn over dt, which is like change in n over change in t, change in population over change in time. This is seen both here and here. So in the problems, they will tell you if it's exponential growth or logistic growth. So let's take a look at it because I think it's easier to see with examples. Okay, we have a population of reindeer experiencing exponential growth. We have a pop size of 250, deaths 40, births 43, deaths 10. We could be asked to calculate the R max. We could be asked how many individuals are added to this generation and how many will be at the next generation. So let's take a look at it. We are going to be using our exponential growth equation, and we're also going to be using this one, y, you'll see in a minute. I always think it's helpful to take my starting data and figure out what variables those stand for. So let's take a look at that. Population size, that's what N stands for. Births are B and deaths are D. And the equation sheet literally has this on it. So if you forget what N is, it tells you its population size, okay? So you don't have to memorize that. So now I see, okay, this R max, to solve for R max, I'm going to need to know N, cool, which I do, and then I'm going to need to know this dN over dt. Well, I mean, I'm not given that, but I am indirectly because dN over dt, how much the population grew by, is equal to births minus deaths. I do know births, I do know deaths. So therefore, I'm going to first find this value and then plug it in right here, and then I'll solve for R max. Okay, that's what I'm going to do. So to find this first value up here, I'm just going to do births minus deaths, 43 minus 10, and that's going to get me 33. Okay, so 43 minus 10 is 33. So now I know this dN over dt. I'm going to plug 33 down in for here. I know my N is 250, and so I'm just going to solve. 33 equals R max times 250. I'm going to divide both sides by 250, and I'm going to get 0.132. So what this means, again, R max is the maximum growth rate. So that means this population can grow by 0.132 or 13.2%. Does that make sense? Like every generation. All right. So that was the first question that was asked. The second question that was asked was, how many individuals are added to the population? Y'all don't make this harder than it is. If we had 43 births and 10 deaths, how many were added? 33. There you go. Easy peasy. Next question. How many individuals will be in the population at the start of the second generation? Okay, so we had 250 and then we added 33. So now we have 283. Great. Easy. If we wanted to know, for example, how many would be in a third generation, here's the math we would do. We would do our growth rate, 0.132, and we would multiply that by our current generation population number, our current N. So we would do 0.132 times 283, and that tells us that it would go up by 37.36, or we'll round it down to 37 because we can't have 0.36 of a reindeer. So that means, okay, 37 reindeer would be added. So 283 plus 37 means we'd have 320 reindeer to start off the next generation. Okay, so that's an example of how to use the exponential growth equation. And now one for the logistic growth. We got a flock of sheep and they're undergoing logistic growth. So again, I always like to go through and figure out what equations I'm using. I'm going to be using my logistic growth equation because um, it's what it said in the question. And let's figure out what variables we already know. This is equal to N. This R max was just told, and carrying capacity is K. So how many individuals are added in the population? We're going to be essentially solving for this. We know R max, we know N, and we know K and N. So we're just going to plug stuff into here. So first we're going to do K minus N divided by K. Then we'll times that by N and times that by R max. Okay, so here we go. So we're going to do 75 minus 30, which is 45. 45 divided by 75. That's the math we do next. 45 divided by 75, which is 0.6. 0.6 times 30 times 0.22 gives me 3.96. You can't have 0.96 of an animal, so we're going to round up. So that means we would add 4 individuals to this population in one generation. Great. So then how many individuals would be the population at the start of the second? We started with 30, we added 4, so 30 plus 4 is 34. Again, if we wanted to see how many individuals would be added in the next generation, I'm just going to do this equation right here, R max times N, K minus N over K. All right, that's all I'm going to do. But this time I'm going to have 34 in here instead of 30. So I do 75 minus 34, take that number divided by 75, multiply it by 34, multiply it by 0.22. That would give me 4.08, so 4. So again, I would add 4 sheep in this generation, which would bring me up to 38 sheep. Okay, so that's how you use those equations. After this now, you're going to have a set of problems in which you're going to work through some of these similar type problems using the math that you've seen here, using your equations, and hopefully now that you've seen some done for you, you'll be able to solve some equations on your own.